Okay, hello again. This last section of your notes on conduction in solids is about electrons and holes. And it's really trying to emphasize to you that the devices operate using both the electrons and holes being important, and that an electron is really more than simply the absence of a hole. This is going to be especially important when we go through the operation of bipolar transistors. And in fact, to really grasp the differences between electrons and holes, we need to be able to accept that both electrons and holes experience wave-like and particle-like properties. And so moving away from the idea that they're following Newtonian mechanics and instead follow quantum mechanical principles as well. So if you, I'm just going to scroll down, if you can read this through. But if you imagine charge carriers as having a waveform such as this one shown here, then you can see that it's got a wave packet, which means it's got both wave-like properties, being from a sine wave, but it also exhibits particle properties too. It forms a small individual pulse. And in this way, a hole can be viewed as a wave packet, I'll just go down, which is out of phase with its corresponding electron packet. But when they're brought together, you can see they're still going to recombine to form nothing. The advantage here is that the wave packets can now exist on their own and can be considered independently. And so for this reason, it's easier to see that they're not simply equal and opposite. For example, we know the effective mass of a hole is considerably greater than the effective mass of an electron. In both cases, their effective mass is unlike the rest mass of free space, and we've got the data for that. But when you bring these small matter together, they behave differently. So if you have lots of electrons, they don't behave as if they're an individual electrons, and vice versa. In fact, if their effective masses are different in different parts of the energy bands, and there's different longitudinal and transverse effective masses as well. These masses are listed on your data sheet for some of the materials. In new developments, engineers try to exploit the different effective masses and different bands in order to optimize or maximize the device performance, because they can be used to make devices faster because the mobility depends on the effective mass. And they can also be used to prevent leakage currents through dielectrics, and we'll be coming on to that as well. So that's just to give you an overview, and I've also got a couple of links that I'll put up just now. So the videos that hopefully you can see on these links will give you some further information about wave-particle duality, as it's known. And you certainly don't need to know everything about quantum mechanics, but some sort of elements are important for understanding the device operations, and the engineers at least won't have covered much of this in stage one. But please note, this is really just for background. There's certainly not going to be exam questions on it, and the same for the videos of the iPhone fabrication that hopefully you will have looked at and read some information about. So that's really the end of this first section on solids, conduction in solids. I've placed a tutorial sheet on Canvas for you, and it's got some questions to help check your understanding once you've gone through all of the material and videos. So if you want to look at this question sheet on your own, please do so before Thursday's tutorial session. That would be great. But if you want help, then come along on Thursday. It'll be great to see some of you there. I'll be posting the answers to the question sheet at the start of the next week so that everyone can have a chance to look at it first. I just think that would be a better way of doing it than making you look at it fresh, but it's really up to you. So while most of the questions on the sheet are similar to those I've gone through in the notes, there is one on there, I think it's the fourth and maybe another one, does tend to get people a little bit stuck because of the need for an equation which isn't in the notes, but it is found on the equation sheet where I said the key equations were going to be. and it's the relationship between the carrier concentration and the separation of the Fermi position with the conduction band. If you remember, the closer the Fermi position is to the conduction band, it's suggesting the more n-type the material will be, and therefore the higher the carrier concentration of electrons in the conduction band. And so the equation that you need to look out for is N is equal to NC e to the minus EF minus EC over kBT, Boltzmann constant and temperature. So hopefully you can see that. That's not it. Right, thank you. Hopefully that will be sufficient for you to work through, and I will see some of you there, or hopefully all of you there, on Thursday.